Section 2.7 Equilibrium, Change, and Reversibility. So first, what is internal equilibrium? That's simply equilibrium inside the system. It can be regarding to the pressure, temperature, or concentration. If the pressure, temperature, and concentration of all components inside the system is exactly the same everywhere, we say the system has reached internal thermodynamic equilibrium. Also, there is equilibrium between the system and its external surroundings, and it may refer to pressure or temperature. When that's the case, P equals P external, T equals T external. Now the definition of the so-called quasi-static process. Quasi-static means the rate of change is negligible. Reversible processes are quasi-static. That means in a reversible process, the rate of change of all thermodynamic functions is negligible. To achieve that, the pressure of the system should be very close to the external pressure. The temperature of the system should be very close to the surrounding temperature or external temperature. In a reversible process, we have dW equals negative P external dV, and then we can replace P external with the system pressure P. In an irreversible process, the difference between external pressure and inside pressure is finite. Therefore, we cannot replace P external with P in the equation to calculate work. Now let's look at a few examples. Processes A and B are irreversible processes. And then you will see process C is reversible. So A 20-liter ideal gas expands to 80 liters. The pressure changes from 4 bar to 1 bar. The external pressure is 1 bar. And then how do we compute the work and heat? B, the same gas expands again all the way to 80 liters and 1 bar. But this is done in 2 steps. First step, there's 20 liters of ideal gas expands to 40 liters against 2 bar external pressure. And then we change the external pressure to 1 bar to allow the system to further expand to 80 liters. How do we compute the amount of work? There are 2 steps. We compute the work for step 1. It's going to be negative 40 bar liters. Step 2, also negative 40 bar liters. Together, work is negative 80. Q is positive 80. In these 2 processes, the system expands against an external pressure that's different from the system pressure. And this kind of processes are called irreversible processes. Now, to be clear, irreversible processes in these calculations means P external is different from P. But later you will see irreversible processes involves the increase of the entropy of the universe. And that's why these processes cannot be reversed. Because to reverse those processes, the entropy of the universe would have to decrease. That's the violation of the second law. Now let's look at one reversible process. In this case, P external equals P. That means this process is reversible. So how do we compute work? This time, we can replace P external with P. And pressure is nRT over V. And then we integrate nRT over V dV. We got this number, negative 111 bar liters. That's W. Q is positive 111. And this is a reversible process. In this process, the entropy of the universe remains unchanged. And also, we can compute the reverse process. Let's say the same gas In the final state, 80 liters and 1 bar is compressed back to the original initial state, 20 liters and 4 bars. That's the initial state. And you will see work is now positive 111, Q is negative 111. So after this cyclic process, work is 0, Q is 0. In this case, again, C and D together is a cyclic process. After this cycle, W is 0, Q is 0, delta U is 0, delta H is 0. And there's no change to the entropy of the universe. And therefore, both C and D are reversible processes.